morning. I'm Horvath. You guys know me already. I'm going to talk to you about plate tectonics and lithospheric plate interactions. So, first we're going to talk about the layers of the Earth. The Earth is composed mainly of the crust, the mantle, and the core. So the crust has the lithosphere and actually part of the asthenosphere in it, as you can see in this picture here. Basically, you've got the inner core, which is solid, the outer core, liquid, and then the mantle is kind of a thick, goopy, more magma-like substance. So that's actually what the lithospheric plates will float on top of. So that's how they move around, that's how they shift, because that mantle is actually the liquid material versus the solid. So what is a tectonic plate? Tectonic plate is different parts of the crust. The lithosphere is the top portion of the crust, and basically it's broken up into different pieces. These pieces can vary in size, shape, density, and also how deep they are. They can be anywhere from like half a kilometer thick to multiple hundreds of kilometers thick, depending on where they are and what they're composed of. As you can see, this picture here kind of demonstrates different plates around the world. You can see how thick they are and the different size and relationship. So what drives tectonic movement is actually convection currents in the mantle. So you can see there's these things they're called convection cells. The core is very hot, so what it's going to do, it's going to heat the magma up that's closer to the core. As that magma rises towards the surface, it's going to start cooling and it's going to transfer energy to the actual lithospheric plates that sit atop the mantle. Also, it can feed a divergent plate and actually form the crustal material, which we'll get into later. But basically, you want to remember that the convection currents move these cells that circulate hot magma up and cool magma back down to be reheated and recycled. So there's three different types of plate boundaries. First is a transform, which is a strike slip boundary. It's what we see in California, San Andreas Fault. Basically, you're going to have two plates sliding past each other. I'll go a little bit more in depth on how they slide past each other, but you can see that there's no inward force and no outward force between the plates. So all the friction is between right here on the plates where they're sliding past each other. It's called a strike slip because they'll hit, sometimes they'll get stuck together, sometimes they'll constantly move, but usually they're going to be stuck, and once that friction is overcome, they'll release a large amount of energy, which is how the earthquakes are. The divergent boundary is a spreading center. Spreading center or a spreading center. So basically, that's where the new magma from the mantle is going to come up and fill that hole that's being left by the plates that are moving apart here. So the asthenosphere you can see, as I referred to, and the lithosphere is on top. Those plates are moving away. Convergent boundaries are usually trenches, so they're found where one plate is subducting underneath. As the plate is subducting, it is going below because it's a more dense material than the plate that stays on top. So you can see here, convergent plate, two plates that come together. Which one goes underneath is going to be determined by how dense it is and also how they hit each other in relation. Plate interactions around the world. This is a rough map of all the different plates around the world. You can see you've got subduction zones, spreading zones, volcanoes, and transform zones. So just looking at the Pacific plate, for example, you can see that one plate has all the different kinds of zones that you can have. Down here, you've got spreading centers or divergent zones. You've got transform boundaries, all these horizontal pieces, and then this whole other coast of the Pacific plate is actually a convergent boundary. So you can see how all of the boundaries are still a part of a single plate. It's not necessarily one type of boundary per plate. So, crustal formation. As I said, when plates are being separated at the divergent boundary, the magma from underneath is actually going to rise and fill that spot. So there's a couple different spreading centers around the world right now. You can see this one here in the Pacific. This is called the East Pacific Route. It's located about 2,000 miles off the coast of South America, and it's the fastest spreading center in the world currently, so therefore it's the most active. It's spreading about 16 centimeters per year in relation to the 5 average centimeters per year of most other ones. You can see it's a little bit hard to tell the years here. This is 0 to 2 million years, 2 to 4 million years, which is the age of the new crustal formation that's been there. So you can compare between the different spreading centers and see how big the rate has been over time. Because the 0 to 4 million year boundary right here is about as much as the whole time range for the Atlantic spreading center. Another thing that I'll get into is actually the Red Sea up here. There's a new spreading center, and that is eventually going to push the plates open and create a new ocean way down the road. So pretty interesting. So there's 3 different kinds of faults that go along with the plate boundaries. The boundaries are the transform, the divergent, and the convergent. And each of these faults will have their own seismic activity, volcanic systems, different things like that. So first, the transform boundary. Transform boundary, as I said, plates slide past one another. So what I meant by I would talk about how they slide past is based on driven by spreading centers here. So as you can see in this depiction, you've got the spreading center right along the center, another spreading center, and another spreading center. When these plates are being pulled apart, it's separated by the actual spreading center, so you can see they're moving at different rates. So right along here, where the plates are in contact, is where the strike slip boundaries or the transform boundaries are going to be. And that's where, depending on the rate of spreading, there can be different amounts of energy released, different seismic in the two. So a divergent boundary is depicted here by the center. What happens is the plates are pulled apart by the subduction, and as they're subducted, they'll melt back in, and I'll get to that in the next slide. So basically, where the plates are pulled apart, this convection cell that I talked about is going to push the warm magma from the mantle up into that space that's left. It's usually under an ocean or underwater. Sometimes it can be on land. An example of that would be Iceland. There's actually a spreading center running through the center of Iceland. And basically, it's going to come up, it's going to hit the water, it's going to solidify and add new crustal material to each plate that's moving apart. So you can see that here, it's kind of uplifted at the the divergent boundary. It's uplifted because that new material is pushed up and created. As the plates pull apart, it can be eroded or kind of slumped down, making sort of a depression zone. Another thing that's interesting that you can find at a divergent boundary is hydrothermal vents. Hydrothermal vents are just areas where heat is being released at the bottom of the ocean. You can often find chemosynthetic organisms there. A lot of times people think that's where life started on Earth because you don't need the sunlight, it's really deep, and you have a lot of energy and elements and minerals that you can use from the water. Alright, so the convergent boundary. Subducting plates are called slabs, I believe I said that. And basically what happens is the slab is determined as the plate that's going under because it is more dense. So what happens here, as you can see, is that after the plate moves down, the plate gets subducted underneath, usually a continental plate. So, oceanic plates are obviously submerged in water. They build up sediment and deposits from runoff on land, and over time, it helps them be more dense and they're filled with water. So usually they're the ones that's going to subduct beneath the continental plate. Here you can see, as it's being subducted, what happens is the heat from the core and the mantle is actually going to start melting the plate. Some of that material is going to be recirculated into the convection cell, and some of the material is actually going to rise as magma plumes. So when it gets hot enough and it melts, sometimes there's chambers that they can fill, other times it superheats different gases that are located within the rock. And that is able to travel to the surface, travel through different separations, heat water, and actually end up fueling active volcanoes. So back to what I was saying about the Red Sea, that's actually a rift valley. And rift valleys form where divergent boundaries take place. What's happening is, as the plates are being pulled apart and new material is being created, you kind of get a little bit of a bump in the center. But as it continues pulling apart, the new material is not being created as high and as elevated as the rest of the material around. So therefore, it kind of becomes depressed. What happens is, these areas usually fill with water, as in the Red Sea. That's a new plate center, so eventually that's going to keep spreading, and become an ocean there. Here you can see you've got a little bit of buildup in the center. As it goes away, it becomes compressed. The yellow here is actually different deposits, sediments, things that have built up on the plate. So it kind of builds back up, but it leaves that valley of the rift valley. So mountain building events. Mountain building is usually associated with the convergent boundary. As that one plate is subducting, sometimes it can push up the less dense plate. It'll actually push up on the bottom, kind of fighting back, I guess, in a sense. And what also happens back to the volcanics, where that magma is rising, you get the superheated plumes that fuel the active volcanoes. So usually if you see a mountain chain along the side of, say, an ocean or where you think plate boundary is, there will often be active volcanic activity. There will be mountain ranges. An example of that is actually it's the Wanda plate. I'll have a picture of it after. But that's subducting underneath Washington. Kind of fuels magma activity in Yellowstone areas like that. The volcanic arc is a string of active volcanoes. It's usually parallel to a convergent boundary. So an example of that would be the South America, where it's actually all converging along the side. So you have a string of volcanoes. It's referred to as a volcanic arc. So there's different kinds of earthquakes. They all come from the different boundaries. Transform boundaries, divergent boundaries, and convergent boundaries, as I said. So the transform boundary, an example is the San Andreas Fault. This is actually along here, right there. And they're usually shallow but powerful. Those are the ones where the plates are sliding past each other. The friction builds up, they slip and slop, and that releases the energy. At divergent boundaries, the rate of earthquakes and the magnitude of them is dependent on the actual spreading rate. And the spreading rate, as I said, depends on where you're located, how much new plate material is being formed, and how fast the plates are being pulled apart. So a fast spreading rate is going to have a bunch of smaller earthquakes. Usually these are undetectable by anybody. Seismic graphs can figure it out, they can see them, but they won't be felt by the normal human. At a slow spreading rate, there's chance for larger earthquakes, because as that material is being created, it often will kind of pile up and fall, things like that, and break up. So just still smaller earthquakes, but a little bit bigger than the fast-moving spreading centers. And convergent boundaries, they have the most powerful earthquakes. They're usually the deepest, but they can be anywhere between basically the surface, where the actual converging boundary is, and say 700 kilometers underneath the ground. Depending on how deep it is, that's when you'll kind of feel it, but if it's a deep one, that's great magnitude, you feel that very well as well. This is a picture of different earthquakes that were recorded, I believe, in 2008 around the world. And you can actually see where a lot of them are focused. The most focus is around convergent zones, if you refer back to that other picture that I showed, which is the next one. So you can see by looking at the earthquakes and the plates, this picture is the plates here, this picture is all the earthquakes. They actually line up almost perfectly. So even without doing a special kind of map or anything like that, you can basically plot all the different kinds of earthquakes, fall along the plate boundaries, and kind of get an idea for what kind of plate boundaries are there as well. So you can see where the most concentrated earthquakes are. Those are convergent boundaries. And you can also see where there's a little bit less and less frequent. That's where the transform and the divergent boundaries are. Alright, so in summary, we talked about the layers of the Earth. You've got the crust, you've got the mantle and the core, parts of that. You've got convection currents are what fuel it all. That's what fuels the new lithospheric material. That's what recirculates the melted past lithospheric material as it is subducted. The different plate interaction actions cause the volcanics. They cause the earthquakes around the world. So it's something that you really want to know about. Kind of helps explain different phenomena that you see. And then earthquakes and volcanism are always interesting to look at. Basically, sources, and does anybody have any questions?